When we're evaluating a limit algebraically, we could be dealing with a function that is defined piecewisely. So if we're dealing with the piecewise function, we just have to remember back to the fact that a limit is what y value we're approaching from the left and from the right. So if I'm trying to evaluate the limit as x approaches 1, that means that from the left of 1, I need to look at the piece at the top, but from the right of 1, I need to look at the piece at the bottom, and if those are the same, so if my limit as x approaches 1 from the left is the same as the limit as x approaches 1 from the right, then I can go ahead and say that the limit does exist and what that value is. So my limit as x approaches 1 from the left is really the same as saying the limit as x approaches 1 of this 2x plus 1, because this would be the left piece to the left of 1. And when I plug in 1, I'm going to get 3. For the piece on the right, I'm really looking at the limit as x approaches 1 for the function 4 minus x squared, which I also get 3. So this is what tells me because we approach the same thing from the left of 1 and from the right of 1, I can finally say here at the end that the limit as x approaches 1 of f of x does in fact equal 3. Okay. I want you to go ahead and try a similar problem on your own. So go ahead and pause the video, see if you can decide if this limit exists and what it is. So finding the limit as x approaches 0 from the left, so looking at that top piece, we should get 4. And then also the limit as x approaches 0 from the right, so the bottom piece, we also get 4, so we should be able to say the limit overall as x approaches 0 of f of x equals 4. By the way, because both of these ended up existing, if from the left it approached 4 and from the right it approached 3, then we would just say that the overall limit does not exist. Just like those examples with our graphs where it looked something like this. I meant to do an open circle there. But where it's approaching one thing from the left and another thing from the right. It is a jump, so it would not exist. The last type of limit that I want to look at today involves the difference quotient. Now, don't get too excited here. I know how much you all love the difference quotient. And this is actually what the difference quotient was created for, was this limit right here. If you go on to calculus, you'll learn that this is actually where a derivative comes from. It's pretty nifty, but for what we're doing, we're just going to evaluate the limit, which means that we're basically going to use the difference quotient. But once we get it down to where, remember, we're wanting the h to cancel with something in the numerator, once that happens, we'll evaluate the limit as h approaches 0. So for the function that we have, our x plus h, remember that we're just replacing the x with an x plus h, so we'll have a 6x plus h. And then subtracting the whole function, so subtracting 5 minus 6x. And then remember that we're always looking for those h's to cancel. So once I simplify some things in the numerator, so distributing that -6 and distributing the negative in the second part, we see that the 6 x's will cancel. We've got a +5 and a -5. So ending up with just 6h over h. Finally, my h's can cancel. They divide to be 1. And then I actually don't have to do much evaluating here. I'm plugging in 0 into nothing, but I will end up with just 6 for the value of my limit. Let's try one that's a little more challenging. So still looking at the difference quotient and finding that limit as h goes to 0. But this time we're looking at something with a radical in it. So when I find that f of x plus h, I will have the radical x plus h minus 2. And then minus our whole function, this radical x minus 2, all over h. So this one is a little trickier to simplify, but just like the other ones that we were dealing with radicals in them, it's a good idea to go ahead and multiply by the conjugate. So we'll have an x plus h minus 2 plus radical x minus 2 over the same thing. And remember, this looks kind of gross, but whenever we multiply a radical by itself, that means I'm just going to end up with what's underneath the radical, so an x plus h minus 2, that I'll end up with the positive and the negative version when I multiply this by negative radical x minus 2, and then the same thing by positive radical x minus 2. I won't have that oi part, so I just have to multiply the last two, and again, they're the same thing, so I will end up with negative, but it's going to be an x minus 2 when I multiply them. And then the denominator, just like we have in the past, we're going to mock multiply, where we have that x plus h minus 2 plus radical x minus 2, all in parentheses. So don't actually multiply that out, because that is going to take you a lot longer and it will not be fun. So now hopefully we can see some things in the numerator that are going to cancel. When I distribute that negative, I'll have an x and then a negative x, so I'm going to go ahead and cancel that. I'll have a negative 2 and then a positive 2, so those will cancel. I'm left with, in the numerator, an h, which is good news. Radical didn't go far enough. Because now I can finally cancel my h's, which allows me to find the limit. So in this case, I do actually have to plug in 0. Remember, I'm plugging it in for the h's, so I will have a 1 in the numerator as a placeholder there, but then I have a square root of x minus 2, and then I didn't have anything to plug it in there, so I've got plus the square root of x minus 2, or we could simplify that a little further to say we have 2 radical x minus 2's, and that is the limit as h approaches 0, and it actually is the derivative of our original function, which you guys will learn more about if you take calculus. Okay, last example, but I do want you to try this one on your own. I don't know what's happening to my marker, but this is an x squared plus 3. Go ahead and pause the video and try one for yourself. So for the first steps of using the difference quotient, make sure you have that whole x plus h squared when we replace the x plus 3, and then minus our whole function x squared plus 3. When we multiply out this x plus h squared, make sure you're multiplying x plus h times x plus h. So we do have to FOIL, we'll end up with that middle term in there, make sure that's there. And then on the right, distributing the negative gives us that negative x squared minus 3. So at this point, our x squared and negative x squared cancel. Our 3 minus 3 equals 0 as well. So looking at what we're left with, remember that our goal is to cancel the h in the bottom with an h in the top. So in this next step, since I'm left with just terms that have h in them, I'll go ahead and factor out an h. So I've got a 2x plus h in parentheses and then over h. It's going to allow me to cancel my h's. And then finally, I can evaluate the limit as h approaches 0 by plugging in 0. We'll get 2x. And that's it. You've made it through your last lesson of distance learning. I just wanted to say thank you for those of you that have been doing this the correct way, watching the videos and actually learning from them, taking notes, working through the homework, and actually trying to understand the concepts rather than just breezing through all of it. I just so appreciate that myself, but also know that having integrity will always be beneficial in the long run. So work through this last practice assignment. We'll have our last assessment on Friday over circles. And then if you have completed everything, then you are done, and have a great summer.